In this video, we will look at solving logarithmic equations. A logarithmic equation is where the variable that you're trying to solve for is inside of a log. We will have 4 steps for solving log equations. We will condense into one log using log properties, where our goal is to have log base of the input is equal to the exponent. The next thing that we're going to do is we're going to rewrite the equation into exponential form. When we do this, the log goes away and we're left with a base raised to the exponent power is equal to the input of the log. Then we will solve for the variable, and step 4 is really important. We want to check your answer back into the original equation. So the original equation is really important. We'll come back to that in a little bit. The overall value inside of each log must be greater than 0. So it must be positive. It goes back to the idea that the domain of log function is from 0 to infinity, but does not include 0. Alright, so let's talk about why that domain is so significant. Alright, so if you type into your calculator log of 0, okay, what does your calculator say? So let's go to Desmos. Alright, let's go to functions and we'll go to log and let's type in 0. And it says undefined. Okay, is that significant to log of 0? What about natural log? What if I do natural log of 0? Go to functions, we'll go to ln, put in 0, also undefined. So why is putting 0 into a log a problem? The answer to that question goes back to the exponential form. When we solve logs, we are asking ourselves this question. We're saying the base of the log, which in this case is 10, raised to what exponent, and so that's what we're looking for the answer for that log, is equal to the input of the log, which in this case is 0. 10 to what power will give us 0? So there is no power that I can raise 10 to get 0. That is an unsolvable problem. Same thing with natural log of 0. The base of the log raised to what exponent is equal to the input of the log. We again have a positive base. There's no way that I can raise that positive base to any power to obtain 0. So there's no solution there. This also, the domain also excludes negative solutions. So what if I have log of -1? Okay, so I go back to the exponential form, 10 to what power would give me to -1, and there's no way that I can take a positive base, raise it to any power, and obtain something negative. It's not going to happen. It doesn't matter what the base of the log is. Let's take a natural log of, let's say, -100. If I was going to solve that, I would say the base of the log raised to what exponent would equal to the input of the log. There is no power that I can put on e that would allow me to get to a -100. So we're not allowed to have negative values inside of logs or 0 inside of a log because there is no solution to those problems. If you were to go to Desmos and try to put in -1 into that log, you would also get undefined. So any negative number inside of a log is going to yield no solution. In this case, Desmos says undefined, but it's not a solution. Alright, so let's look at some examples of solving logarithmic equations using these 4 steps. For example 1, we're asked to solve. We're asked to give an exact answer and also an approximate decimal solution. Our decimal values should be rounded to the nearest 3 decimal places. Step number 1 is log form. We want to make sure that our equation is written so that we have one log by itself on one side. We can identify the base, the input, and we have a number on the other side that we call the exponent. And when we look at our equation, we see that that's already done. We have one log by itself on one side, we have the input, and we have the exponent on the other side of the equal sign. So what I want to do is I want to identify what is the base, what is the input, and what is the exponent here. We should have only one answer for each of those categories. The base, we have ln. Remember, the base of that is the natural base e. The input is x plus 5. The exponent on the other side of the equal sign is 4. Step 2 is to rewrite this in exponential form, which is the base raised to the exponent power is equal to the input of the log. Alright, so the base we said was e. The exponent is 4 is equal to the input of the log, which is x plus 5. Alright, step 3, we want to solve for x. So I want to get x by itself on one side. So to do that, I'm going to subtract 5. So minus 5 from both sides. And I get e to the power of 4 minus 5 is equal to x. Step 4, we want to check our answer in the original equation. Really important that you do not check in any form of the equation except the original. Go back to before you did anything at all to the original printed problem. And I'm going to replace x with our solution. So I'm going to put everything here into our equation in place of x. All right, and I'm going to simplify. The 5's will cancel. I'm left with e to the positive power of 4. Essentially, when I simplify, I want to make sure that this quantity is always going to be something positive. E to the power of 4, we have a positive base raised to a positive power. That's definitely going to be greater than 0. So that solution checks out. If you want, you can put that into Desmos. Alright, so here we have Desmos. I'm going to pull up the keyboard, go to the alphabet, I'm going to find the E, raise that to the power of 4. So if I wasn't sure if that was positive or not, or greater than 0, I could always put that into Desmos and check that. Now our final answer is what's here in yellow where we solve for x. So let's get a decimal approximation of that. It's e to the positive 4 power. Okay, make sure you come out of the exponent and then we'll say minus 5. So the decimal approximation for our final answer is about 49.598. We're asked to round to the nearest 3 decimal places. Alright, so our exact answer is actually e to the positive 4 power minus 5. We're also asked to give an approximate answer, and that was the 49.598 when rounded to the nearest 3 decimal places. Alright, let's look at example 2. We have 3 plus the natural log of the square root of x minus 4 is equal to 7. Our first step is to rewrite this to make sure that it's in log form. We want log, we want to have the base, we want the input for that log, and then the number on the other side is always recognized as the exponent. Right now we do not have one log by itself on one side. In order to accomplish that, we need to get rid of the 3. So I'm going to subtract the 3 from both sides. So now I have natural log. The square root of x minus 4 is equal to a positive 4. Alright, so now I have one log by itself on one side, nothing in front of it. We can identify that the base of this log is e. The input of this log is the square root of x minus 4, and the exponent is that positive 4 on the other side of the equal sign. So step 2 now, we can rearrange those 3 things into exponential form. We want the base raised to the exponent is equal to the input of the log. Right, so the base is e, the exponent is 4, and then the input of the log is the square root of x minus 4. Once it's in exponential form, then we're going to solve for x. So we want to get x by itself on one side. So let's look here. We want to get this alone on one side. We have a couple of things we need to do then. We need to get rid of the square root, and we also need to get rid of that minus 4. Okay, so I'm just going to copy our equation over here. so we can look at solving for x. Alright, so to get rid of the square root, I'm going to square both sides. Okay, so 4 times 2, we're going to use that power rule for exponents. If we do a power to a power, we can multiply those exponents. So I get e to the 8th equals, the square and the square root are going to cancel out, and I'm left with x minus 4. Okay, still trying to get x by itself, so I'm going to add 4 to both sides. So our final answer is e to the 8th power plus 4 is equal to x. Alright, we want to check our answer in the original equation. I'm going to leave a little room where x is, and I'm going to replace that x with our answer. So our answer was e to the 8th plus 4, and so that's what I'm going to put in place of x in the original equation. Alright, we want to make sure that what's in the overall input of that log turns out to be greater than 0. So let's do a little simplification there. Positive 4 minus 4, that leaves me with e to the 8th. Okay, the square root of e to the 8th is what I have left over after I simplify. And just to prove that that is overall a positive input, I'm going to go back to Desmos. Right, let's do the square root of e. And then I'm going to raise that to the power of 8. So overall, that is a positive input that gets left inside of the input of that log. So our solution checks out. We just want to make sure that it's a positive value that gets left in the input of that log once we simplify. Alright, so what is our final answer here? Okay, we want an exact answer and also an approximate answer. Our exact answer is e to the 8th power plus 4. Our approximate answer, let's put that into Desmos altogether, e to the 8th plus 4, and see what we get. Make sure that you come out of that exponent and make sure you do a big plus 4. Alright, so I'm going to write 2,984 point, and I'm going to go 3 places out, and we're going to look at the 4th one and say, does that round that 3rd decimal place up or keep it the same? And it looks like it's going to round it up. So I'm going to do 958. In example 3, we want to put our equation into log form. We want one log by itself on one side. We want to be able to identify the one base, the one input, and the one exponent on the other side of the equal sign. When we look at this problem, we have 2 logs, but we want to look for ways of simplifying in the easiest way possible, and also the most efficient way possible. So in this problem, when I look at the 2nd log, I see that I can actually use the inverse property to simplify that to get rid of the log. The base of the log and the base of the input of that log match, and if they match, they get to cancel each other out, and I'm actually left with a 3. So we were able to get rid of that log with a really simple property that we already know. Let's simplify a little bit more now. 3 minus 1 is 2. Now our goal is to have one log by itself on one side with nothing in front of it and nothing behind it, just log, base, and the input. Right now we have a 4 that's multiplied times the front of that log. Now there's a couple of different ways you could deal with that. One way would be to put the 4 back on as the power on that input. But if I do that, then I get this equation that I have to solve that has a power of 4, so at some point I'm going to have to take like a 4th root of both sides, and I really don't want to have to go there. Is there a simpler way that we could solve this problem without obtaining a power of 4? So Let's look at what operations we have. We have 4 times the natural log of x minus 1 equals 2. What undoes that multiplication? Well, the easiest thing I could do would be to divide both sides by 4. So that's what I'm going to do, and that actually gives us a much simpler equation to work with. Okay, so there's our log form. If it's in log form, then I should be able to identify the 1 base, the 1 input, and the 1 exponent. The base is e, the input for that log is x minus 1, and the exponent is 1/2. So we're going to take that log form now and rewrite it into exponential form. And remember, that's the base raised to the exponent is equal to the input of the log. So that's going to be e raised to the power of 1/2 is equal to the input, which we said was x minus 1. Alright, so step 3 now, we want to solve for x. Okay, to solve for x, all I have to do is add 1 to both sides. So I get e to the 1/2 power plus 1 is equal to x. Okay, before we decide that that is for sure our solution, we want to make sure that we check our answer in the original equation. Alright, so I've rewritten my original equation, and in place of x, I am going to put our solution, e to the 1/2 power plus 1. And let's simplify that and make sure that what's inside of this log stays greater than 0. Okay, so the plus 1 and the minus 1 will cancel each other out. I'm left with e to the 1/2 power. So when I look at all of the logs in my equation, I have e to the 1/2 power, which is greater than 0, and I have e cubed, which is also greater than 0. So all of the logs have a positive input, and so our solution checks out. Okay, so what is our final answer? Our exact answer will be e to the 1/2 power plus 1. Our approximate solution for that, let's go to Desmos. So looking at my keyboard, I'm going to put e to the power of, and I'm going to do 1 divided by 2. Make sure that's all up there in the exponent. Come out of the exponent. Make sure that you're putting in a big plus 1 outside of that exponent. And I get about 2.6487. We want to keep the nearest 3 decimal places, so the 7 is going to round the 8 up to a 9. Alright, so our final answer is exactly e to the 1/2 power plus 1, and that's approximately a decimal value of 2.649. Alright, so the key to this problem is taking care of that really easy simplification and dividing by the number in front of the natural log instead of putting it on as the power. Try to keep this equation as simple as possible when you're solving it. For our fourth log equation, we're going to go to step 1 again. Step 1 is to get the equation into log form. We want 1 log by itself on one side, and we want to be able to identify the 1 base, the 1 input, and is equal to the 1 exponent on the other side of the equal sign. Right now we have 2 logs, and I notice that I'm adding in between those 2 logs and they have the same base. So we're going to use the product rule to condense. Alright, so the product rule says that we can take those 2 inputs and we can multiply them together inside of the same log of the same base. Alright, so now we have 1 log by itself on one side, we have a base, and we know the input, the 1 input, and we have the exponent on the other side. Now let's simplify a little bit before we move on. I'm just going to go ahead and actually multiply out what's on the inside. So foiling, right? First times the first gives me x squared. Outer times the outer gives me a positive 3. Inner times the inner is a positive 4x. Last times the last is a positive 12. And we can even simplify a little bit more than that, right? So let's go ahead and just combine those like terms in the middle to get 7x. Okay, so step 2 would be to now take that log form and convert it to exponential form. So that means we want the base raised to the exponent is equal to the input of the log. So the base of this log is 6. The input is the x squared plus 7x plus 12. And the exponent is the 1. So when I go to convert the base, you have 6 raised to the power of 1 is equal to the x squared plus 7x plus 12. Okay, 6 to the power of 1 is just 6, so we'll try to simplify that in the easiest way that we can. Alright, step 3 is to solve for x. So in this case, we are solving a quadratic equation, and I'm going to try the factoring method. To try the factoring method, you have to get 0 by itself on one side first. So I would subtract 6 from both sides first. Sometimes we call this the zero product theorem. First you get the 0, then you have to have a product, which means you need to factor that trinomial. So that's x and x. Let's go for 1 and 6, both positive. You can check that by multiplying it out. Make sure you get back up to x squared plus 7x plus 6. Alright, and then once you have it factored correctly, then set each one of those factors equal to 0 and solve for x. So I get x equals negative 6 and x equals negative 1. Now it's really important here that you take those solutions and you don't assume that they both work, but you want to make sure that you check them both in the original equation. So I'm going to write down the equation, and I'm going to replace x with our solutions. Alright, we have to check one at a time. So I'm going to check negative 6 first. If I plug in a negative 6 in place of x in the original equation, for this input I get a negative 2. So already we have a problem. That input is an overall negative value, but what we're required to have is that all of our inputs have to be greater than 0. Negative 2 is not greater than 0, so x equals negative 6 is not a true solution. You'll see in some books they'll call this an extraneous solution, and you see the word extra there. So it is actually not a true solution because it does not work in the very original equation that we were asked to solve. Alright, what about x equals negative 1? Now some people assume, well, that one is not going to work because it's negative. Well, let's try. Let's plug it back into the original equation and see what happens. Alright, so everywhere that I have an x, I'm going to put a negative 1. Okay, the overall input in the first log is going to be a positive 3. That's good to go. The overall input in the second log is going to be a positive 2. That's good to go. So we never said that we cannot have negative solutions. So be careful there. What we said is that we're not allowed to have a solution that when it gets plugged into the log, that it makes the overall input into that log turn out to be negative. As long as the inputs of those logs turn out to be overall greater than 0, then we're good to go. So our final answer here is x equals negative 1. Alright, example 5, again we're solving a log equation. So the first thing I want to do is to get the equation into log form, which means I want one log by itself on one side, And I want to be able to identify the base, the input, and the exponent on the other side of the equal sign. I want to make sure I have only one of each of those. Alright, so when I look up here, I see that I have two logs. But this time I'm subtracting in between, and so this represents that quotient rule. So to condense this down into one log, I'm going to write log base 5. But since I'm subtracting straight line, I will be dividing inside of that single log. The positive log is going to have the top of the fraction. The negative log is going to give me the bottom of the fraction. Alright, so now we have one log by itself on one side, and we can identify that the base is 5. The input of this log is that fraction, 2x divided by x minus 3, and the exponent is the 3. Alright, so step 2 then, we're going to convert that log form into exponential form, which means we want the base raised to the exponent is equal to the input of the log. So the base of this log is 5, the exponent is 3, and that's equal to the 2x divided by x minus 3. Right? Is there any simplification we can do? I'd like to do that before I move on to the next step. 5 to the power of 3 is 125. So I'm going to go ahead and simplify that before I start to solve for x. Okay, when I go to solve for x here, I notice that I have a fraction. And if I have one fraction equals one fraction, then I can actually use cross multiplication to solve for x. So I'm going to think about 125 as a fraction by putting it over 1. And then I'm going to do a process called cross multiplication. To cross multiply, you take the top of one fraction and you multiply it times the bottom of the fraction on the other side of the equal sign. 2x times 1, that gives me 2x. And that tells me a quantity on the left side of the equal sign. And then I'm going to multiply in the other direction. The top of the left fraction times the bottom of the right fraction. So that's 125 times x minus 3. Right? Notice how I put that in parentheses? Because I want to make sure that the 125 gets multiplied times the x and also times the negative 3. Right, that gives me a negative 375. Right, now I have a linear equation. Notice that I don't have x squared, I just have x to the power of 1. So to solve a linear equation, I just want to get x by itself on one side. So we'll do all of our adding and subtracting first. Gather all the x's up to one side. So I'll do that by subtracting 125x from both sides. On the right side, I just have a number, negative 375. On the left side, I have negative 123x. Okay, you're welcome to put that into your calculator. Then I'm going to divide by whatever's in front of x. Alright, I'm going to simplify that. We have two negatives. Two negatives always gives me a positive. And I'm going to leave my answer exactly as that fraction. Now we do want to make sure that we check our answer in the original before we declare that to be our final answer. So I'm going to go back up here and I'm going to rewrite my original equation. Okay, so my original equation is up here, log base 5 of 2x minus log base 5 of x minus 3 equals 3. So I'm just going to copy that over here under step 4. Okay, there that is. Now I'm going to take the solution that I received and I'm going to put that everywhere that x used to be in the original equation. Alright, and then we're going to look at, is this going to be something greater than 0? A positive number to a positive number, I really don't even care what it is, I just want to make sure that it's greater than 0. And that definitely is greater than 0. Two positive numbers multiplied together have to get something positive. What about 375 divided by 123 minus 3? Now for that, I may not know off the top of my head. Let's just go and check that in Desmos. Alright, gives me a really small positive number, but it's still a positive number, so we are good to go. Alright, so that answer checks out, and so our final answer then is declared to be 375 divided by 123. Now if you want to, you could say that's your exact solution. Approximately, what is that value? Once again, we can go back to decimals. So that answer is approximately 3.048. We'll take the fourth number after the decimal place and use that to decide if the third decimal place gets rounded up or stays the same. So in this case, it looks like it's going to get rounded up. So 3.049 approximately. Alright, so there's our final answer. For example 6, we're asked to solve this log equation. We're going to go back to step 1 again. We want to make sure our equation is in log form first. So we want 1 log, 1 base, 1 input by itself on one side equals exponent on the other side. It looks like here we have 2 different logs, and we would like to combine them into 1 log. So we're going to condense, and we notice that we're subtracting between those 2 logs. So we have 1 positive log and 1 negative log. So we're going to use the quotient rule to condense these into 1 log. So we're going to condense into 1 log of the same base. The input in the positive log goes at the top of a fraction. The input in the negative log is going to go in the bottom of the fraction. So now we have 1 log by itself on one side. The base of this log is e. The input of this log is that fraction x divided by x plus 5, and the exponent is 3. Alright, so step 2 would be to convert this into exponential form, which means we want to rewrite it as the base raised to the exponent is equal to the input of the log. The base of this log is e. The exponent we said was 3, and the input of the log is the x divided by x plus 5. Now we are asked to give an exact answer and also an approximate answer. Because we wanted an exact answer, I'm not going to put e to the positive 3 power in my calculator. As soon as I do that, I actually enter into the realm of an approximation. So I don't want to do that. So I'm going to leave it exactly as it is, and we're going to solve for x, and we're going to make sure that we keep things exact. We don't round until the very end. In order to solve this, we have a fraction on one side, and we can solve using cross multiplication if we have one fraction equaling another fraction. So I'm going to make both sides look like fractions, and then I'm going to cross multiply. So x times 1 gives me x. E to the power of 3 times x plus 5 on the right hand side. And then I'm going to distribute the e cubed. I'm going to keep it as e to the power of 3 there. So that's e to the power of 3 times x plus 5 times e to the power of 3. Okay, so the order really doesn't matter. Usually we like to keep the variables in the back and the numbers out front, but it doesn't really matter. Now we want to solve for x. So we have an x here on the left side, and I also have an x on the right side. So we're going to use a little trick here to help us get that one x by itself on one side that we're trying to solve for. So we're going to bring all of the x terms to the same side, and I'm going to do that by subtracting e cubed times x from both sides of our equation. So all the x terms on one side, anything that doesn't have an x in it, I'm going to move to the other side. So those cancel out, and I'm left with 5 times e cubed. So that has no x in it. That's just a number. I want to keep that on the right hand side, and everything else is going to move to the left hand side. Now a key thing here is that those are not like terms, so I can't combine them and keep it exact at the same time. So I'm not going to combine them. We're going to do a little trick again. So we are going to notice that we have x and x. We have an x in both terms. We are going to factor out an x. So we have an x here and x here. It's a common factor. So I'm going to write that as x times, that's 1 minus e to the power of 3. Now you can check your factorization by multiplying the x back into both terms, redistributing it, and make sure you get what's above. Now, why is that a nice little trick? Well, we had two x's before. We wanted one x, we wanted it by itself on one side. We brought all the x's to the same side, but we had two of them. So I wanted to get only one x, and the kind of the tricky way to do that is to think of it as factoring x out of both of those terms. So now we have only one x. We have x times that group. Well, I want to get x by itself. Well, then let's divide by that group. We're going to do that on both sides. So now that cancels on the left side, and on the right side I'm left with x is equal to, and now the right side is just a number. It has no variables in it. So this will be called an exact solution. If you leave e raised to that power without putting it into your calculator to find that decimal approximation, this would be our exact solution. Now before we decide that it actually is our solution, let's go back and let's do step 4, and that is to check our answer in the original equation. So if we go back to our original equation that's up here, it's natural log of x minus natural log of x plus 5 equals 3. Remember, we want to plug this solution in place of x and see if it comes back positive or negative. We want to make sure that that value overall is greater than 0. Okay, so I have copied the equation here. So everywhere that I had an x before, kind of left a blank spot there, and I'm going to type in my solution. Right, so I want to make sure that the overall value of that input is greater than 0. So let's go to Desmos. So we'll type in 5, and then e to the power of 3. Right, I'm going to just highlight all of that, make sure that stays at the top of the fraction. I'm going to hit divided by. Then I'm going to do 1 minus e to the power of 3. So it turns out that the overall value of that fraction is a negative value. So if this turns out to be something that's negative, that's less than 0. Our rule is that that overall input has to be greater than 0. So that does not work. If it doesn't work there, it really doesn't matter what happens anywhere else. It has to work everywhere. So if it fails in one place, then it fails for the entire equation. Now, if this solution had worked, then we would put this in a box, and then we would go to find an approximation of that solution. All right. So make sure that you're still aware of that process that we use to find that exact solution, even though in this case it didn't work. So what happens when we have one solution and we try it and it doesn't work in the original equation? If all of the solutions that you get do not work in the original equation and you end up crossing out all solutions, then your answer is no solution for this equation. So the one solution that we did get turned out to be extraneous. We ruled out all solutions, so there is no solution that we were able to find for this equation. In example 7, we're solving a log equation. The first step for solving a log equation is to rewrite the equation in log form. So we want one log with one base, with one input on the left-hand side, and on the right-hand side we want to get our exponent. So in this case we have two different logs that are being added together. If I add between two logs of the same base, then I can put them together or condense them using the product rule. Right, so that means that I'm going to put them together into one log, or I'm multiplying between those inputs. Okay, let's do a little simplification there. We have x times x plus 2, so that's x squared plus 2x. Step 2 is to take that log form and rewrite it into exponential form, which means we want to take the base, raise it to the exponent power, set it equal to the input of the log. So what is the base of this log? Well, that's e. The input of this log is x squared plus 2x, and then the exponent is the 4 on the other side of that equal sign. So let's rewrite it in exponential form. The base of the log, e, the exponent is 4, equal to x squared plus 2x. And so now we're going to solve for x. Since we have x squared in the problem, we're solving a quadratic equation. We have a couple of different methods that we can use. One of them would be to try to factor it. If it doesn't factor, then we know that we can go to the quadratic formula. Both of those methods require that we get everything on one side and 0 on the other. So I am going to bring the e to the positive 4 power to the right-hand side. So I'm going to subtract that from both sides. So I get 0 is equal to x squared plus 2x minus e to the positive 4 power. Okay, so that is not going to factor because of the e to the positive 4 power. That's going to mess up my factoring technique and make things more complicated. So I'm just going to go for the quadratic formula. To use the quadratic formula, we have x is equal to negative b plus or minus the square root b squared minus 4 times a times c all over 2a. Okay, so what's the a and the b and the c? So the number in front of the quadratic term, or the number in front of x squared, that's the a value. So that's an implied 1. The number in front of just the x term, or x to the power of 1, that's the b term. And whatever is the constant, the term that doesn't have x in it at all, that's the c. So now we have negative b, so that's negative 2, plus or minus b squared, minus 4 times a, which is 1, times c, which is a negative e to that positive 4 power, all of that divided by 2 times a, which is 1. So remember, we want to keep our answer exact until the very end, and then we'll find an approximation. So I get negative 2 plus or minus the square root, that's 4. We have a negative 4 times 1 times negative e to the positive 4 power. A negative times a negative is going to give me a positive, and that's 4 times e to the positive 4 power, all over 2. Now that would be our exact solution. Now remember, before we decide that that is our official solution, we do want to make sure that we check it in the original equation. Alright, so here's our original equation. Natural log of x plus natural log of x plus 2 equals 4. So I've copied that here. And now we're going to take that solution and we're going to plug it in everywhere that we had an x before. Alright, I definitely don't know what that is off the top of my head, so I'm going to plug that into Desmos. Alright, so that's negative 2. Let's do the positive value first. Remember, we do officially have 2 solutions here, so let's check each one separately. So I'm going to do the plus. I'm going to get square root 4 plus 4 times e to the power of 4. I'm going to highlight all of that to make sure I divide all of that by 2. So it looks like the positive sign in between is going to work for both of these. So that gives me a positive 6/4 4, 5, and so on. Remember, all I really care about is that it's greater than 0. And this is going to take that about positive 6.45 or so and then add 2 to it. So that definitely checks out. So the positive solution is definitely going to work. Now what about the negative solution? Let's try that. So let's say I put a minus there. So the minus one actually isn't going to work, right? Because we see that this would give me a negative 8.45 approximately and so on. And we are not allowed to have one of our logs with a negative overall input. So if the negative one doesn't work there, then it's also not going to work here as well. Remember, we rule out any solution that causes any of the logs to have a negative input. Right? So that one doesn't work. So our final answer here is going to be that positive solution. Alright, so that would be the exact value. What about the approximate value of x? So let's go back to that. Let's put our plus sign there again. And so our approximate value is 6.456 rounded to the nearest 3 decimal places. Alright, so you want to make sure that you can work on getting that exact value that has not been rounded, and then also make sure you can type that into your calculator and find an approximation.